All right, so in this section, we will be talking about three things: sequences, series, and geometric series. So everything we're going to talk about in this unit is going to be based off of sequences. So we're going to start off with a very quick overview of what a sequence is. And in reality, it's just a list of numbers. However, this notation here, we need to be comfortable with. Each of these terms are the terms of the sequence. So A1 is the first term, A2 is the second term, A3 is the third term. So an infinite sequence will have something that looks like this, where we say we start at n equals 1 for the first term and go to infinity. And so it's an infinite list of numbers, and a sub n is how you can generate the sequence if it's written as an explicit formula. So usually we will be working with explicit definitions. You've seen recursive definitions before, so I'll go over a couple quick examples, but everything we have will be an explicit definition because it lets us find any term in a sequence like A50 or A40. So here are two examples of explicit formulas for an infinite sequence, and it asks us to find the first four terms. So the first term, A1, we'll just plug in 1 for n, so we'll have 1 over 2 to the 1, and that will be 1/2. A2, or the second term, will be 1 over 2 squared, which is 1 over 4. A3 will be the third term, so plugging in 3 for n, 1 over 2 to the third, so that'll be 1 over 8. And a sub 4 will be 1 over 2 to the fourth, which is 1 over 16. So this sequence here is the sequence that starts at 1/2, and then the next term is 1/4, and then the next term is 1/8, and the next term is 1/16. And we could keep going, right? This is an infinite sequence, but it only asked us to list the first four terms. This other sequence here is interesting because of this -1 to the n. This is going to change each term from being positive and negative, because when n is odd, a -1 to the odd power will be negative, and when n is even, -1 to the n power will be positive. So here, a sub 1 will be -1 to the 1 times 1 over 1 squared plus 1. So that'll be a -1 in the top. 1 squared plus 1 is 2. So a sub 2 will be -1 squared, so now that's going to become a positive 1 times 2 over 2 squared plus 1. So that'll be a positive 2 over 5. So A3, -1 cubed will be a negative, and then we'll have 3 in the top, and then 3 squared plus 1 will be 10. And then A4, the fourth term, -1 to the fourth will be positive, so now we'll have 4 in the top. 4 squared plus 1 will be 17. So this is the sequence -1/2, 2/5, -3/10, 4/17, etc., etc., etc. And this will happen all of the time. This will be something we'll see that will cause our terms to alternate. So that's important. And you can see that here in the graphs. These are the sequences. Remember, sequence is just a list of numbers. Sure, there's a function that you could use to define these numbers, which does come into play later, right? But we're just looking at the fixed numbers, right? So there's dots. They're not a continuous line, right? These are not continuous. There's only a fixed list of numbers. But you can see how over here they alternate between positive, negative, positive, negative, positive, negative. But they're still getting closer and closer to 0, which we'll point out in a little bit here is important. So let's just real quick look at a couple more explicit definitions. Just in case we have to write the explicit definition, I will also give you the recursive definition here. You don't really need to know how to write those. Those are not really important for us, but just so you understand what they mean. So here, the recursive formula for this, we are adding 7 each time to get to the next term. So the recursive definition would say the first term, A1, is -2, and then every term after that, AN, will be every term after that, AN plus 1, so every next term will be defined by the term in front of it. So AN plus 1 will be 1 more than the term before, and so AN will be the term before, and then you'll add 7. So what we really care about is the explicit formulas here, and if we're adding 7 each time, right, we're talking about a linear change. So we will say that any term an will be generated by 7 times the previous term, so n minus 1, the previous term number, and then we'll have to add the -2 that we started with. So you might like it better as -2 first, and then each time we'll add 7. And so we're going to do that for n minus 1, because the first time to get from -2 to 5, you're just going to add 7. The second time you'll add 7 again, and 7 again, 7 2 more times, and 3 more times, etc., etc. Over here with this sequence, we are now multiplying by a number to get to the next one. So we're multiplying by 2 each time here. And so this is a geometric sequence now because we're not adding, but we're multiplying. Recursive definition would say, okay, B1, the first term is 3. And then each next term, so n plus 1, will be the term before n, and then times 2. So since we're multiplying by 2 each time, that's the recursive definition. Now we don't really care about that. We really care about the explicit version. So any term an. Well, in order to figure out what this looks like, let's look at what's happening here. So first term is 3. Second term is 3 times 2. Then the next term is that term, 3 times 2 times another 2. And then the next term is that term, so 3 times 2 times 2, the previous term, times another 2. And then the next term is that term times another 2. So really what we have here are powers of 2, right? We have 2 to the first, 2 to the second, 2 to the third, ... And this first one even has 2 to the 0 power. So here we're starting with our general term Bn will be 3 times some power of 2, right? First time is 0, right? So if n, we're starting with n equals 1 usually, then you would start with n minus 1 up here to get 0 for your first one, and then 1, 2, 3, and beyond. So this is a geometric sequence, and we'll come back to these later because they are important, but they generate geometric series. So now let's talk about a limit of a sequence, because this is probably the most important part here, is the limit of a sequence. What does that mean? Well, we can already see that these two sequences up here that we just looked at, let's go back to those. The terms are getting bigger in both of these as we go along. So we would say these do not have a limit because they keep growing. However, if we look at one of our previous ones here, the first example we looked at, 1/2, this guy right here, 1/2, 1/4, 1/8, 1/16, those are getting smaller and getting closer and closer to 0. So those do have a limit, and we would say that converges. So a sequence will converge or diverge if the sequence is approaching a value. So what does that actually mean? Well, that means if you have the general term and you do the limit as n approaches infinity of that general term, that explicit formula, and that equals some value, then it converges. If that limit does not exist, then it diverges. So this is why the explicit formulas are so important. So we have two series here generated by two explicit formulas. And let's go ahead and look at what, I'll just kind of tell you very briefly what the first couple terms are here. So here, A1, if you were to plug in 1, you would get -1/2. If you were to plug in 2 for n, you get 1/5. Plug in 3 for n, you get -1/10. Plug in 4 for n, and you get 1/17. So these are the first 4 terms. And as you can see, it looks like, even though they're going back and forth between positive, negative, the numbers are getting closer and closer to 0. The fractions are getting smaller. So it would seem as though this sequence converges to 0. But how do we actually show that? Well, we take this explicit formula and we do the limit as n approaches infinity of this an, this general term, And as we do that, this top term, when n is even, it will be positive. When n is odd, it will be negative. So this will go back and forth between 1. But then this one will continue to grow. The bottom will continue to get bigger and bigger and bigger. So if the fraction is if the bottom is getting bigger and bigger and bigger, and the top is just staying at 1, going back and forth between negative and positive, we will get closer and closer to 0. So this limit equals 0, and so we would say the sequence converges because the limit exists. This sequence over here, let's look at the first couple terms. We'll actually do this one out because it's an important one. So the first term, cosine of 1 pi, or just pi, will be -1. Second term, b2, cosine of 2 pi, we're just plugging in the values for n, will be 1. b3, cosine of 3 pi, back around to the other side of the unit circle, so -1 again, and then b4 will be cosine of 4 pi equals 1. So this sequence is literally just the numbers -1, 1, -1, 1, -1, 1. So as you can see, it probably doesn't approach a value, right? It just keeps going back and forth between -1 and 1. So we would think that this diverges, which is true. It does, but how would we show that with calculus? Well, we're going to take the general term here, bn, and we're going to take the limit of this as n approaches infinity. Well, as n goes to infinity, cosine oscillates, right? It oscillates back and forth and between -1 and 1. So this oscillates, and so the limit does not exist. So then we would say that this sequence diverges. So this is how we use the calculus to show that the sequence converges or diverges. So you just do the limit as n approaches infinity of this general term. That's why it's so important to have the explicit formula for a sequence. Okay, so now let's talk about a series. So a series is similar to a sequence in that we create a series from a sequence. And this whole entire unit is going to be all about series, different types of series. So this is the most important part of today. So we are going to talk about what a series is. So a series here is going to be a list of numbers that you're adding together. So you take your sequence, and now you add up all the terms. And so we say the summation notation says we start at the first term, k equals 1, and we add up all the terms to infinity of whatever sequence here, ak, we're talking about, okay? So we have these things called partial sums. S sub n is the sequence of partial sums. S sub n is just the sum of the first n terms. So S sub 1 is the sum of the first term. S sub 2 is the first 2 terms added together. S sub 3 is the first 3 terms added together. And so S sub n is the first n terms added together. And this is important because this is going to help us understand what a series, whether a series converges or diverges. So I'm going to show you an example here to start. So we're going to take the sequence here, an. We'll start with a sequence. And we're going to say an, the general term here, is 1 over 2n. So this is an explicit formula. So this sequence will be a sub 1 will be 1 over 2. A sub 2 will be 1 over 2 squared, so 1 over 4. A sub 3 will be 1 over 8. And so the sequence that we're looking at right here is 1 over 2, 1 over 4, 1 over 8. That's the sequence. Now we're going to create a series from this sequence. We'll start at n equals 1 and goes to infinity of this guy right here. So we'll often see this written as so. And so the series will be adding up all of these terms. So 1/2 plus 1/4 plus 1/8 plus dot, 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 dot. So the series is adding up all of these terms in this sequence, but the sequence is going to generate your terms. So that's why it goes right there. So now let's talk about what these partial sums are. So S sub 1 is just the first term. S sub 2 is the first 2 terms added up. So that will be 1/2 plus 1/4. S sub 3 is the first 3 terms added up. And if we look at what these sums are, so the first term is obviously just 1/2. If you add 1/2 and 1/4, you get 3/4. Add 1/2 plus 1/4 plus 1/8, and you get 7/8. And so S sub n would be if we did this up till the nth term. So we added up the first n terms. So if you take a look here, 1/2, 3/4, 7/8, these numbers here, the sums themselves, if you create a sequence out of those, it looks like those are approaching a value. It looks like those are getting closer and closer and closer to 1. And so S sub n, the nth term, if you notice a pattern here, the 1/2, 3/4, 7/8. So the number on the bottom is 1 bigger than the number on the top, and the bottom number are powers of 2. So this is very difficult to kind of notice this pattern and create it yourself. So you won't have to do this very often. But if we look here, the bottom number, 2, 4, 8, those are all powers of 2. So that's going to be 2 to the nth power. And then the top is just 1 less than that, 2 to the n minus 1. So if we were looking at like the S sub 7th, first 7 terms added together, then that'll be 2 to the 7th minus 1 over 2 to the 7th. But we don't really care about that. So, but what you can notice is that 1/2, 3/4, 7/8, even though I'm adding a number each time to get to that bigger number, the numbers are getting closer and closer to 1. And if we were to keep going, then each fraction is going to get closer and closer to 1. Even though we're adding numbers, it's not going to ever go over 1. It's going to keep getting closer and closer to 1. And we can see that if we do the limit of this S sub n. And since, as n goes to infinity, since 2 to the n and 2 to the n are both exponentials growing at about the same rate, right, we would look at the leading coefficients, which are just invisible ones here. So this will just be 1 over 1, or just 1. And since that limit is equal to 1, then we say this series from n equals 1 to infinity of 1 over 2 to the n converges. And the sum is 1. So even though we're adding up lots and lots and lots of numbers here, each time, even though you're adding up infinitely many numbers, the sum will never go over 1. In fact, it's going to get closer and closer to 1. So we say this infinite sum equals 1. We say the series converges. So 2 important things to take note here. A sub n, a sequence converges. When the limit as n approaches infinity of a sub n exists. And a series converges if the limit as n approaches infinity of these partial sums exists, S sub n. So A sub n and S sub n are 2 different things. So you could have a series that converges and a sequence that converges, but you could also have a sequence that converges and the series diverges. So we're going to explore that. Writing this formula for this S sub n is going to be tricky a lot of the times. We'll look at one more example here and then we'll talk about what happens if we can't write that formula. But this is how we know if a series converges. So let's look at one more example here. So here we have a series. So this is your A sub k or A sub n. They're the same thing, just using a different index here. So we start at 1 and go all the way to infinity. So we're going to find the first 4 terms of the sequence of partial sums. So the sequence of partial sums is S sub n. So we want the first 4 terms of that. So we want S sub 1, S sub 2, S sub 3, and S sub 4. So we'll start with S sub 1. So S sub 1 will be just the first term. So we're going to plug in k equals 1 into this. So we'll have 1 over 1 times 1 plus 1, which will be 1 over 1 times 2, or 1/2. For S sub 2, we're going to use that number, plus we're going to plug in 2 into this guy to get the second term in the sequence. So 1 over 2 times 2 plus 1. So this will be our first term, 1/2, plus 1 over 2 times 3, which is 1/6. And if we add those together, we'll get 3/4. So then S sub 3 will be the first 3 terms added together. So we know that's 1/2, 1/6. We found that from the previous one, right? First 2 terms. And now we're going to add on the third term. So we're going to plug 3 into this. So I have 1 over 3 times 3 plus 1. So that'll be our first 2 terms, which are 1/2 plus 1/6 plus 3 times 4 is 12. Add all of that up and you'll get 4/5. I'm sorry. That's 3/4. This last one is, sorry, I can't do my math. This last one is 2/3. And then S sub 4 will be the first 4 terms added up. So it'll be 1/2 plus 1/6 plus 1/12 plus now at our fourth term we'll be plugging 4 into this. So it'll be 1 over 4 times 4 plus 1 or 5. So that'll be 1 over 20. So add those up and you'll get 4/5. So then if we look at this sequence of partial sums, the sequence of partial sums, S sub n, is the sequence of all these sums. So the first sum is 1/2. The second sum is 2/3. The first 3 terms is 3/4. The first 4 terms added up is 4/5. And this will continue forever. And you can see that you probably think the series converges because if we look at these partial sum sequence, 1/2, 2/3, 3/4, 4/5, these are getting bigger, but they're getting closer and closer to 1. And here, this one's a little bit easier to write a formula for S sub n because the top number is just n. So the 1, 2, 3, 4, 5 in the top, and then 2, 3, 4, 5 is just one number bigger. So n over n plus 1. So here, that's your formula for S sub n. And so if you want to show with calculus that the series converges, we'll show that the limit as n approaches infinity of S sub n, or the limit as n approaches infinity of n over n plus 1, which these grow at the same rate because they're both the 1 power, so you just look at the ratio of leading coefficients, which is 1, so this will also be 1. So this series converges and equals 1. So we'll say it converges, and we'll even go up here at the top here, and we can say that this series equals 1, because the series converges, because the limit of S sub n is equal to 1, a limit exists, so the sum of these infinite numbers, no matter how long we keep adding numbers to this sequence, the sum will add up, get it closer and closer and closer to 1. Okay, so again, finding this formula for S sub n is not the easiest thing in the world. And in the future, what's going to happen is we're not going to actually do that very often, having to write a formula for S sub n and take the limit as n approaches infinity of that, because that can be very hard to do. So instead, we're going to have all sorts of different types of series, and we're going to say, okay, if this types of series, and we're going to have tests for the different types of series, and we're going to say, if you have a series that looks like this, it will converge if so-and-so and so-and-so, or diverge if so-and-so and so-and-so, instead of having to write these formulas. But it's good to understand that that's the basics, and you do need to know that. So the first test that we're going to look at is for the geometric series, which you've seen before in Algebra 2, and we've even talked about it. So it's when you're multiplying a number by another number. So we looked at an example like this earlier. This was our geometric series from earlier, when each term you're multiplying by 2. So you're doing 2 to multiplying by another 2. So you have powers of 2. So this is the general form of a geometric series. When you have a, some constant in front, you have r, a common ratio raised to the nth power. And if you have a geometric series like that, it's really easy to tell if it converges or diverges. All you need to know is the absolute value of r. Whatever that common ratio is that's being raised to the nth power, if that r is bigger than or equal to 1, the series will diverge. if that r is between 0 and 1, the absolute value of that, so a fraction between 0 and 1, then the series will converge, and in fact, we have a formula to calculate the sum. It'll be whatever that constant a is divided by 1 minus the common ratio. And we're going to look at a couple examples of this. Here, note that this definition only applies when n is equal to 0 for the sum here. Okay, the converging or diverging applies anytime the ratio is less than 1, but for the sum, this formula only works when n is equal to 0. So what if it does not begin with an index of n equals 0? Well, you can still find the sum, and you can still just worry about r being less than 1, but a more intuitive way to think about it is just to think that a in the top needs to be just the first term of the series divided by 1 minus common ratio if n is not equal to 0. Which, if n is equal to 0, it will still be the first term when you plug in n equals 0. That will give you a. But that's a good way to remember that. So this is important here. Okay, so let's look at some examples of geometric series. So this first one, we're going to see whether or not this is a geometric series. That's all we're going to do here. This guy is a fraction raised to the nth power. It's not infinite. It just adds up the first 10 terms, starting with n equals 1. But it's still a geometric series. It's just not infinite geometric series. Because it's a ratio raised to the nth power, this is a geometric series. B, however, is not a geometric series because we don't have a ratio raised to the nth power. N is in the denominator. This is actually called the harmonic series. And we'll talk about that later, but this is not a geometric series. And this one here is also not geometric because you don't have a ratio raised to the nth power. So now let's look at some geometric series and let's see if we can figure out if they converge or diverge. So you're looking for a ratio raised to the nth power, and that's going to be your r. And then a is constant in front, right? So you've got this form for a geometric series, right? So you're looking for what a and r are. So this guy here is geometric. We can see that because we've got something raised to the nth power. So this r here is 1.1. And we're looking to see if the absolute value of r, which here, the absolute value of 1.1 is just 1.1, and we want to see if that's greater than or less than 1. So if it is greater than 1, then it diverges. That's what we said. And this is greater than 1. For B here, we have something raised to the nth power, but this one's a little interesting because it has a negative. So we do want to rewrite that without the negative in order to really look at what we're looking at. So we'll rewrite this as 1 over e to the n, or that's the same thing as 1 over e to the n, because 1 to the n is just 1. Okay, so that's a nice little trick. So here now, if we look at that, we do have something raised to the nth power. So here r will be 1 over e. And we want to see if the absolute value of r is greater than or less than or equal to 1. So if it's equal to 1, it also diverges. So if our absolute value r is greater than or equal to 1, we diverge. And if the absolute value of r is less than 1, we converge. That's what we're looking for. So here, e is 2.7, so 1 divided by 2.7 will definitely be less than 1. So this converges, and then to find the sum, we're going to use that formula. Because we start at n equals 0, we can just use a over 1 minus r, because a will be the first term. And we just need to find a. That's just the number in the front, which here there's just a little invisible 1. So here a is 1. So to find the sum, we'll just do 1 over 1 minus r, which is 1 over e. If you multiply top and bottom by e, you'll get 1 over e over e minus 1. So you might see the answer like that. And this is about, let's look at the decimal version of this, is about 1.5819 ... So it converges, and this is the sum. Let's look at C here. This is clearly a geometric series, something raised to the nth power. This is your constant in front, so that's your A. So we want to see the absolute value of R. which that is going to be just 0.75 because we don't care about the negative, we're looking at the absolute value, and that is less than 1, so this converges. And let's figure out what it converges to. So the sum here, this, because n is equal to 1, we're going to look for the sum being the first term over 1 minus the common ratio. So the first term here will be when n is equal to 1. So a sub 1 will be the first term. So that'll be 3 times negative 0.75 to the 1. And so it will be 3 times negative 0.75 to the 1 over 1 minus r, which r here is going to be negative 0.75. And if we do that math, we'll get negative 9 over 7, which is about negative 1.2857, dot, dot, dot. This guy here is still a geometric series because you still have something raised to the nth power. We just are going to have to rewrite it in some nice ways to see what a and r are. So if we write this as 3 times 1 over 2 to the n, and then we can rewrite this as 3 times 1 over 2 to the n, because 1 to the n is just 1. Now we can clearly see that r is 1/2 and a is 3. The absolute value of r is 1/2, which is less than 1. So this converges. And to find the sum, we'll start at 0 here. So we just need a over 1 minus r. And that will be 6. D is also clearly a geometric series because we have a ratio raised to the nth power. So we'll look at a is 1 here, r is 3/5 or 3/2. The absolute value of r here is going to be 3/2, which is greater than 1. So this diverges. So we can't find the sum then. Here, also clearly another geometric series. A is equal to 1, constant in front. R is equal to e over pi. So then the absolute value of r, e is 2.7, pi is 3.1, so this will be less than 1. So this converges. And if we find the sum, that'll be equal to a, because we start at 0, over 1 minus r. Multiply top and bottom by pi, and you'll get pi over pi minus e, which is about 7.4214. There's one more example here that you will see us do a couple of examples, and it's a way to write a decimal as a geometric series. So if you have a repeating decimal, you can break it down into a bunch of decimals, and those are all thousandths or tenths or whatever. So then we can rewrite them as powers, and then we have a series. So this series has this 1 in the front, and then we see we have 25 in the top of everything, and then this is raised to an n power here. And so we have, you can this n kind of got away here. So we're going to start with n equals 1 and raise it to the power of that. And so then you could always find the sum because r is equal to 1 over 100. And a is equal to 2.5. Since r is less than 1, you know it converges, and then you could say the sum is equal to the first term, because the bottom is 1, over 1 minus r. So the first term here, when you plug in n equals 1, you'll get 2.5 times 1 over 100 to the 1 power, and then 1 minus r will be 1 over 100, and if you plug that in, you'll get 203 divided by 198. And this last type of series here is a telescoping series. This is not on the AP Calculus exam, but it is in most Calculus 2 courses, so if you're moving on, you will see this. So I'm going to include the little QR code here for you to watch a little video on that if you're interested.